Hello guys, this is Paul McWhorter with TopTechBoy.com, and we're here today with episode number 51 in our incredible new tutorial series where you are unleashing the power of your Raspberry Pi Pico W. What I will need you to do is pour yourself a nice tall glass of ice cold coffee. That would be straight up black coffee, poured over ice, no sugar, no sweeteners, none needed. And as you're pouring your coffee, as always, I want to give a shout out to our friends over at Sunfounder. Sunfounder is actually sponsoring this most excellent series of video lessons. And in this class, we will be using the Kepler kit for Raspberry Pi Pico W. Now, most of you guys probably already have your gear, but if you don't, look down in the description. There is a link over to Amazon, and you can hop on over there and pick your kit up. And believe me, your life and my life are going to be a whole lot easier if we are working on identical hardware. But enough of this shameless self-promotion. Let's jump in and talk about what I'm going to teach you today. What I'm going to do is I'm going to show you my solution to the homework assignment that I gave in lesson number 50. But I must first ask, how many of you guys were successful? If you were successful, comment down below, I am legend, double chest bump. And if you were not successful, leave a comment down below. I folded up like a cheap Walmart lawn chair. Okay, hopefully you guys got this, because really it was just pulling together the stuff that we've learned in the last lessons. And what the homework assignment was to take the work that we did last week, where we were getting the kind of ultimate measurements from the MPU6050, right? We were measuring acceleration, we were measuring from the gyroscopes, and then we were fusing the data together to get something that was fast, it was accurate, and it was low noise. And then we added the kind of cherry on the top of the ice cream by also pushing out those long-term steady-state drift terms. So we have something now that is really quite possibly about the most accurate measurements that you can get from the MPU6050 for roll and pitch. Okay, so we got all that. But now what we want to do is we want to make a useful little widget, a useful little gizmo. And so what your homework was, was to actually, I should probably get out of your way, was to actually come in now and use that algorithm that we developed for the MPU6050, but then to connect the OLED 1306 and to have a useful little gizmo where you have like a reticle and then you have a bubble, and that bubble moves around indicating how far off you were from level. So it would be kind of like a 2D carpenter's level. So you could see in my level in the pitch direction and my level in the roll direction. Now, as you all know, with the carpenter's level, you're just eyeballing a bubble. And that's good for qualitative, indication of level. And we do have that. We have a little bubble moving around. But we also want a quantitative, indication. So we also want to actually print out on the little screen roll and pitch. Okay, so way too much introductory talking. Let's jump in and let's see if we can get this thing done. I don't want to start all the way from scratch. And you remember a few lessons ago, we actually did this with the OLED, and we did it just doing sort of a simple measurement of roll and pitch without putting all the bells and whistles in to get rid of noise and get rid of acceleration errors and drift errors and all that sort of stuff. But it did sort of run the OLED. And so I think that would be a good place to start. So I will need you to go to the most excellent www.toptechboy.com. I need you to use this happy little search icon and search on something like 2-axis tilt meter from the MPU6050. And you can see here, this is our schematic of how we hooked it together. We've got the MPU6050 and the OLED 1306 connected to the Raspberry Pi Pico W. And then this was the code that we had developed. Let's see. I'm not sure that copied it, so I'm going to copy it the old-fashioned way. like this, right mouse click, copy. Now we're going to come over to Thonny and let's go ahead and paste it in Thonny. And now let's run it and let's come over here and okay, it seems to be getting data. And I think you can see that all right. Okay, let me go ahead and let me give you the full view here of it. And what you can see is I think this is just getting an approximation of tilt and roll just from the accelerometers. But look at what we have. We have this circle indicating the bubble, and when it is right over the reticle, that means you are completely level in both axes. Then we're printing out the pitch in degrees, and we're printing out the roll in degrees. And then as I tilt it, what you can see as I tilt it, I get a visual indication qualitatively from the little circle moving around. And then I get a quantitative indication from the printouts up there. So how cool is that? Well, is this not the perfect solution? Well, what's the problem? If I have a little vibration, do you see how that bubble is interpreting the vibration and the motion? It's interpreting vibration and motion as changes in tilt, and that would be an error. So if this was on something like a Jeep that you're going off-road in and wanting to measure what your inclination is as you're driving, what would be the problem? If you were bumping, this would be all over the place. Or worse, if you were doing something like a quadcopter, that your approximation of the tilt and roll, the pitch and roll of your quadcopter would be impacted by vibration, and certainly there would be a lot of vibration there. So we spent, what, 4 or 5 lessons getting rid of all the noise, getting rid of all the errors, getting rid of all the short-term errors, long-term errors, all of that. Now we want to come back here and put that better understanding of pitch and roll into this program that I might say quite nicely is already displaying a simple pitch and roll. Okay, so what we're going to do is we're going to come in here and we're just going to jump in one thing. I guess I should show you what I'm doing here, huh? And I think that'll be okay. I think you'll be able to see the code and the live view here at the same time. So we'll leave it there. Well, first of all, we know that on this code, we were just getting the pitch and roll from the accelerometer, but we know that we're going to need that gyro data. So let's go ahead and let's get this, the accelerometer measurements, and the gyro measurements are very similar. So I'm just going to cut and paste those. And then here, this is going to be X gyro, and that is going to be MPU gyro X, then this is going to be Y gyro, and this is going to be MPU dot gyro Y, and then this is going to be Z gyro, that's the measurement, and that is going to be G YRO, gyro. Okay, so now I've got those measurements made, so that's good. Okay, then let's see here. We've got, this is that code that defines the circle. That's good. All that looks good. So now we're just trying to get a better measurement for pitch and roll. And so now I've got this pitch here. Okay, and what I want this to do is I want this to be the pitch from the accelerometer, because now I'm going to have a pitch from the accelerometer, a pitch from the gyro, or a pitch from the accelerometer, a pitch from the gyro, and a roll from the accelerometer, and a roll from the gyro. Also, I don't want to add this other variable, so I'm just going to go ahead and I'm going to convert. Remember, this returns an answer in radians, and I want to work in degrees, and so I'm going to add out here this divide by 2 pi and multiply by 360, and now my pitch A and my roll A will be in degrees instead of radians. Now I can get rid of this code here. Okay, like that. So now I have my pitch accelerometer and I have my roll accelerometer. And then what I'm going to do now is I'm going to come over and I am going to calculate a compensated value, and that compensated, or applying a complementary filter, is going to get rid of all the noise in pitch A and roll A. So I'm just going to call this roll compensated, where I'm going to do all my magic in one line of code. So the pitch, so the roll compensated is going to be the roll. It's funny how I did pitch roll and then I did roll pitch. That's not good. Let me do pitch roll, pitch roll. So now pitch with the complementary filter, we're going to apply that complementary filter. Well, we're always going to anchor things. We are always going to anchor things to the pitch from the accelerometer data, because we always know that in the end, that's the right answer. So we're going to say that we're going to always be listening to that, but we don't trust it in the short term. So we are going to put kind of like, this would be sort of like a low pass filter on it. We're only going to trust it to 0.5%, which means we've got to keep seeing results from it before we trust it. Okay, like that. And then what are we going to get our short-term data from? Our short-term data is going to be 99.5%, 0.995, and that is going to be what? That is going to be, here's where we apply the complementary filter from the roll, the complementary filter on the roll. Okay, that's what we're calculating. Roll, what am I saying? Pitch. That would give a jumbled up mess, wouldn't it? The complementary filter on the pitch, what it was before, plus what? The x gyro, which is going to give me the angular velocity, and then times what? Times t loop, the time that it takes to go through the loop. So it's the old complementary filter value plus the angular velocity times the loop time, and then that whole thing I'm going to trust to 99.5%, but then for 0.5%, I'm always going to look back at my friend, the accelerometer. And so I think this one is going to be very similar, so I think I'll just cut it and paste it here like this, and roll comp is going to be roll. If this doesn't make sense, go back and watch the last few lessons. Roll, and then this would be the Y gyro. Okay, now I've got this loop time, but if I'm going to use loop time, I better define loop time. So I'm going to come up here, and before my loop, I'm going to just set it, I've got to initialize it, t loop is equal to 0, and while I'm doing that, I better also initialize roll with the complementary filter is 0, and pitch with the complementary filter is 0. And now I've got to start my stopwatch. So I've got to start my stopwatch. So how do I do that? T start, I'm going to start timing is equal to time.ticks in milliseconds, like that. That's the number of milliseconds since the epoch. I've started my timer. Okay, now I've got to end my timer all the way down here at the bottom, and I don't think I'm going to put any delay in this one this time, because I've got updating that screen is going to take enough delays, so I'm not going to add any other delays in there. So now what I'm going to do is I'm going to say t stop, and that similarly is going to be time.ticks underscore milliseconds, like that, and that's the time since the epoch. Now the epoch was something like January 1st, midnight 1970, something like that. Okay, but you don't have to worry because I'm subtracting the two, so really what I'm getting here is elapsed time, and specifically what that loop time would be, that would be equal to t stop that I just measured minus t start that I measured at the first of the loop. This reports in milliseconds. I want to work in seconds, so I need to multiply milliseconds by 0.001 to have my units now in seconds. Hopefully that makes sense. Okay, so look, I think I've got this pitch compensated, roll compensated. Okay, let's just see if that is going to work. I just want to kind of look at it here and just make sure that I'm getting kind of good data. And let's see, do I do a print in here anywhere? I think I'll just turn this print on. And then what I'm just going to do is I'm going to have pitch from the accelerometer, and then I'm going to have roll from the accelerometer, and then this is going to be pitch from the accelerometer, and this is going to be roll from the accelerometer, and then I am going to get pitch compensated, and then I am going to get pitch compensated, okay, and then I am going to get roll compensated, and then I'm going to print roll compensated. So what I should see now is, does it work, and is the filter working like I would like it to? So let's go ahead and run this, find out how many errors we PC isn't defined. Oh yeah, so this is pitch accelerometer, roll accelerometer, and then this is pitch compensated, and then this is roll compensated, like that. Okay, that's why I like to run my programs as I'm going. Pitch degrees isn't defined in line 45. Okay, and what I need to do here is I need to change this to my new variable name, which is compensated, and roll compensated. Sometimes when you borrow old code, you've got to adjust things a little bit. Okay, now let's come in and run it. Let's see what other problems we have here. Roll comp needs an uppercase C. All right, here we go. Okay, pitch degrees again in line 50. We use that thing again in line 50. We're just going to take that whole line out because we don't need other print statements slowing us up in here. Okay, and same thing here, pitch degrees should be pitch compensated because that's our final corrected value, pitch compensated, and then roll compensated using the complementary filter. And now let's go. Okay, we are off to the races. And so let me see if I can make this big here, and we seem to have something not real good happening with green, and green is the pitch from the accelerometer. How could we have an error so quickly in here like that? So it really looks like that pitch gyro is drifting, and it is just taking off to the races. And so much so that this tying back to our anchor, the accelerometer at 0.5% isn't enough because that runaway gyro is taking us off course. However, I think there might be something else going on. Let's try running it again and let's see what happens. See if it happens again. Okay, yeah, that green, which is the compensated pitch, that compensated pitch is taking off. The pitch is working, but the compensated pitch is taking off. Let's look at roll. Also, I see I have another problem in roll, and we had corrected this last week, but we need to do it again here. You see that the roll that we're getting from the accelerometer is opposite from the roll that we're getting from the gyro. So remember what we did to fix that. We came up here to the MPU wide gyro, and we made that negative. So let's see if we can take care of that. Okay. Now, that's looking good, but now we still have that really big drift problem. This is what's happening. What's happened this week from last week? We've added this thing where we're going through this big circle 360 times to draw the circle every step. And then we're also moving all of this data to the frame buffer, and then we're sending it a command to show. And all of that is really, really, really impacting our timing. Okay, all of that is really, really, really impacting our timing. So yeah, every single time through the loop, we want to calculate this thing, but we don't want to do all this other stuff every time because, you know, for us to get a good measurement, we're measuring the angular velocity and then multiplying it by the change in time and then adding that to our previous angular position. And therefore, we've got to be real snappy and we've got to be attending to that calculation, and we can't be off doing all this other stuff. So what I'm going to try here, I'm going to say count is equal to count plus 1. So I'm going to put a little counter here. And I'm not going to do the print, and I'm not going to do the display every single time. So I'm going to say now if CNT equal, like let's just do it every 10th time and see how that works. Then if count is equal to 10, then we'll do all this other stuff. But it'll only be every 10th time that we'll draw the circle and do the printing and do the showing like that. Okay, and then down here we need to reset the counter to count equals 0 like that. And now let's run this thing and see if that, you know, kind of allows us to have a little bit more accurate timing and not be out fooling with the displaying and the printing so much. So let's look at it. Count is defined. Yep, up here I've got to initialize it. CNT equals 0. So now let's come in and run it. Okay. The green is kind of taking off again, but not nearly so bad. Okay, it looks like it's kind of stabilizing at about 10 degrees instead of 50 degrees. What if we took this and said like every 15? Then that would allow us to keep track of our timing even more precisely. Okay, it went to about, yeah, I think this is going to be a little bit better doing it like this. Okay, but now what you see is the problem here is now the display is getting kind of sluggish. So we're going to have to go back to 10. And when we go back to 10, what are we going to have? When we go back to 10, what are we going to have? Hopefully you guys see I'm kind of letting you think through this on purpose. Okay, so now if I look at that green is the complementary filter on the pitch axis, and it looks like we've got about a 10-degree error. What kind of error? A long-term steady state error. How do we deal with a long-term steady state error? The little trick that we used last week that I had not added in this week yet, right? It was creating that idea of an integrated error, steady state error, and then squeezing that error out. So let's go back and let's do that. Okay, let's squeeze out that integrated error. And what we're going to do is we're going to come up here and we're going to be good and do it this time before we error. We're going to have an error in the pitch, and that's going to be start out at 0, and an error in the roll, and that's going to start out at 0 like that. Okay, now we are going to come down here. And now what we're going to do is we're going to say, what is that error P and what is that error roll? Okay, what are those two errors? Let's work on that. Did I do it up here? Yeah, I put it there. Okay, so now let's do it. The error P, right, we want to keep adding the error. We're carrying the whole burden of all the errors. And what do we do? What does that mean? We're going to take the error before, and now we're going to add to it. So every time there's a little error, it's like our burden gets bigger because we're accumulating the sum of all the errors. So the new error in the pitch is the old error plus what? Plus what? The pitch from the accelerometer, which is the exact answer, minus the pitch with the complementary filter, and then how long did we have that error? T loop, like that. And now the error roll is going to be equal to error roll plus what? The exact answer, roll accelerometer minus roll comp times T loop. Now what we need to do is we need to go back and we need to add that error back in, or some fraction of that error back in, and then we're in effect we're squeezing out that error. So let's say that that's going to be plus pitch plus error pitch, and let's just say times 0.002. So it's going to take a little while to squeeze it out, but it will always be squeezing out. Okay, now plus error roll times 0.002. Now, we're doing like every time through the loop, we're taking out 0.2% of the error, of that long-term error. We're squeezing it out. Well, if we squeezed it out faster, it would get out faster, but then it would overshoot and have to come back, and it would sit there and oscillate. And so let's try 0.02 and see how that looks. Let's see if we can squeeze it out reasonably. Now, remember, what we're going to see here is we're going to see that pitch. I think, was it green was the pitch? We're going to see it start going away because of that drift term. It's going to start running away because of that drift term in the gyro. But then this error compensation is going to say, whoa, slow down, not so fast. Let's come back to where we know we're supposed to be. So let's watch it here, okay? So what we're going to do is we're going to turn it on, and there it goes. I'm going to let it auto scale, and then I'll run it again so that we can see it a little better, okay? Now we're watching the green, right? We're watching the green. That's the pitch compensated. And what does it do? It's running away, but now our error correction says, whoa, you see it didn't get to -10. That error correction, that long-term squeezing out of the error brings the green. It's going to bring it back to the blue. Okay, there wasn't this same problem. There wasn't this same problem in the roll. It's just in the pitch, and I find that interesting. It makes me kind of wonder, is something going goofy with my sensor? But what did we do? We compensated it out. Now let's see how this thing behaves. Okay, so I'm going to pitch and look at that. That is a beautiful pitch. Okay, and the compensated caught up with the accelerometer beautifully. Okay, beautifully, working well. Now let's see how we're doing on vibration. So you're going to see the blue vibrate, but the green is rock solid. The blue vibrates, but the green is rock solid. Now let's try roll. They're going in the right direction. They're looking really good. Okay, and now let's see what happens. You see the orange is from the accelerometer, and it's all over the place, but the red is holding steady. Okay, you see the red is holding steady, and the red is not misled by the vibration. You see how the red is very steady. Okay. Okay, that looks really good, right? That looks really good. I mean, that is saying that our device is behaving as it should behave. I mean, the raw data is behaving like it should. And I think those parameters are looking pretty good. I think the parameters are looking pretty good. You see it's nice. Probably, you guys, if you could see it real time with me, it would probably be a little better. So you see I roll, and that red is just really nice in the roll. I'm getting very smooth data. And the pitch is behaving very well too. And then when it just sits there, all those values are going back to 0. Okay, that is looking just really, really, really good. But now what we haven't done is we haven't gone in and really looked at the display to see what's happening on the display. Okay, so what I'm going to do to look at that display, at this point, I don't want to slow this thing up any further than it already is. And so I'm going to take the print statement out, and then I don't have any delays in there. That's good. Let's see, I'm wondering if I could even say that we go 0 to 360. What if we tried to go in steps of 2, and then maybe that would speed that part up a little bit. So we've done just a couple of little things. I guess if I want to check the 2 thing, I need to put the print back in. We're just going to kind of tweak this a little bit here. So we're going to come in, and I'm going to run it. Okay, yeah, I think it might be running quicker now. Okay. Yeah, I do think that not spending so much time creating that circle might have sped it up a little bit. Okay, so now let's see. Now I'm going to take the print out. Like I said, I'm going to take the print out as I said, and now I'm going to stop. Okay, and now this time when I run it, we're going to come over here and let's look at this Okay, let's look at this, and now let's run it, okay? And so now this would be kind of like our final device, right? Now, what do you see? The bubbles going off to the right. Why? That is the drift in that pitch gyro. That's the drift in that pitch gyro. And which gyro was that? That was the X gyro. Okay, that was the X gyro. So it's drifting off, but then our error compensation drives the error out, and now we are here. And this is saying that we have a roll of -1.2, and sometimes that's just, you see that this isn't exactly, this kind of wobbles a little bit, so you could be off by a degree. But now let's go nose up, and when we go nose up, boom, look at that. Very, very stable. Nose down, nose up, it says we're at 10 degrees, which looks about right. We'll go back to 0 degrees. You see, and it's not drifting around like it was right when we started the program. That is getting our control system locked in, and you could see that it took 10-15 seconds to do that. And now let's look at roll. The roll looks really good. Let's look at roll and pitch. And that looks really good. And man, look at this. This thing is behaving extremely well. And what you're going to say maybe is you're going to say, well, it looks like that it is behaving about like it was when you started. Okay, but what did we do when we started? We were vibrating, and that bubble was moving all over the place. Now, when we vibrate, what happens? That bubble is rock solid. Or if I tilt it, you see, rock solid, I come back and it pops right back. Boom. Guys, man, I really hope that I did not make you guys weary by going through this. But you see, I just know the tools that I had as an engineer that were just like magic. I want you to get those tools in your toolbox. And this project was not about the MPU6050. It was about thinking like an engineer. It was about thinking like an engineer. And you're never going to get a perfect sensor that gives you perfect data. So you've got to have these tools to work in the real world where the data is never perfect. What did we learn? We learned how to use a low-pass filter. We learned how to use a high-pass filter. We learned how to do a complementary filter. And then we learned how to squeeze out long-term steady-state errors. And those are going to be useful no matter what type of project you pursue in the future. Anything that's going to have a sensor, those are going to be useful. Okay, so now let's talk a little bit. That's all I'm going to do with this project because I think we've had a lot of fun. We've learned a lot. It's time to move on to something new. But what are some directions that you could go with this? One direction that I could think that you could go with it would be to have this tilt meter such that you were operating it as a server and you were interacting with it wirelessly. So like that if you're doing something in one place, you could be in another place and monitoring what the level or what the tilt was. That might be an interesting thing to take this and do Wi-Fi. Like I say, I'm not going to go there because you guys are probably already weary with me on that, but that's one direction you could go. Another direction you could go, you guys that have done Fusion 360 and have a 3D printer, what you could do is, there was one other thing I should show you here. The final little step here I'll do real quick is we can save the program as main. And so let me come over here. And what I'm going to do is I am going to save this on the Raspberry Pi Pico as main.py. Okay, I'm going to save it as main.py. Okay, so there it is. And now what I want you to watch is I am going to come over here and now I'm going to unplug it. And now I'm going to get my handy little battery and the really slick little power control unit that came in the SunFounder kit. I'm going to plug that in, and now what we can see is completely untethered. This thing has come to life. You can see it's going to take 10 or 15 seconds for it to calibrate out. I think that The other thing I would do to this program, you guys can do it if you want. You could not display the first 10 or 15 seconds and just say calibrating, and that way you don't confuse them, because once it gets here, it works. But then you see, look at this. Wow, we are mobile, we are wireless, and we are getting really perfectly rock solid operation. So what did I say? Well, I think I unplugged that as I was shaking it and it restarted. This, I found this connection can be a little loose, and I found like putting a rubber band around it so that it doesn't glitch out is a good thing to do. So one thing you could do is make this wireless and report back to a Python running on your PC or on your phone. That would be one thing. The other thing that you could do is you guys that have done Fusion 360 and have a 3D printer, you could maybe get a small breadboard and then create a little case, and then you could have sort of like a portable unit that you could carry around in your pocket and maybe actually do some useful things with it. Okay, man, like I say, I worry that I've made you guys weary. You leave me feedback below. Do you just want to just write simple programs, or do you really want to look under the hood and understand what it's like to solve real world problems, where you go from something working on your bench top to something that would actually work in a real world application? Let me know if I went a bridge too far on this, or if you really enjoy getting down into the nitty gritty of this level of detail. Let me know. Guys, I hope you're having as much fun taking these classes as I am making them. I want to take a second and give a shout out to you guys who are helping me out over at Patreon. You guys are keeping me in the game. It's YouTube has made it clear that they don't like grumpy old men talking about educational type of things. They want silly, short little clips of people doing silly things, and that's where their advertising revenue is going, and that's where they're trying to steer their audience. And so I'm really doing very poorly as far as the advertising revenue and stuff. You guys that are supporting me on Patreon, you're the guys that keep me coming back week after week after week. Thank you. You all can also help me by giving me a thumbs up on the video. Also helps if you leave a comment down below. If you haven't already, subscribe to the channel. When you do, ring that bell so you'll get notifications when future lessons drop. And as always, share this video with other people, because the world needs more people coding and fewer people sitting around watching silly cat videos. Paul McWhorter with TopTechBoy.com. I will talk to you guys later.